Hey there, I'm DevPoodle. Sokoban is a long-running series of puzzle games that's probably inspired a game you like. Basically, you're a little construction worker guy moving along a grid, whose job it is to push crates around into the right spots, indicated by these markers on the ground. It might seem simple, but it's the foundation of the genre that includes games like Baba Is You, Patrick's Pear Box, Isles of Sea and Sky, and many more. Today I'll show you the creation of a simple Sokoban game using Godot. The end result will look something like this: a player you can move around, walls you can collide with, boxes you can push, and an undo button that lets you rewind all the way back to the beginning. It should serve as a good starting point for a more complex project. So let's get right into it. This is a new Godot project. I've changed a few project settings to make it look nicer. Here's what they are. I also have all the textures I'm going to use already in my project. I made these myself and there's a link to download them below, but you could always choose to make your own. We'll need sprites for the player, the crates they'll push around, and the walls we'll use to make sure they can never escape us. A great resource for free art to use in your game is Kenney.nl, which I'll also leave a link to. Let's create a new script called Movable. It's going to extend Node2D and have its own unique class name. Everything in our game that can move will inherit this class. For now, it will have one member, tile, which represents the grid tile the object is on. This will correlate directly with the cells of a tile map that we'll make later on. In the ready function, we first set tile equal to position divided by 16, because I'm using tiles that are all 16 by 16 pixels. Then, we set position equal to tile times 16, plus a vector 2 with the values 8, 8. You might wonder what this additional offset is for. Because of the way tile maps work, if we were to just set position to tile times 16, then we'd get something like this, where the player is displayed at one of the corners of the grid. So we have to add a small offset to make sure it's centered properly. Then, we can get to defining this class's functions. First, canMove, which will take in a direction and return a boolean saying whether or not the object is able to move that way. For now, it will just return true. Second, move, which takes in a direction and passes it to a function called slide. Slide will add the direction to the current tile, then update the position of the node, just like how we did in our ready function. You might wonder why move and slide are two separate functions. It'll make more sense later when we add an undo button, which will slide objects around but shouldn't be counted as a new move. Now we can make our Sokoban character controller. Let's create a new movable scene called player, drag in our player sprite, and add a new script. The movable class will be doing most of the work for us, so all this script needs to do is handle the player's input. The event parameter here corresponds to some sort of input by the player. We don't really care about when keys are released, so if the event isn't being actively pressed, we'll return early. Otherwise, we want to get a direction based on what key is being pressed. Using a match case on the event as text, let's list all of the events we care about: up, down, left, right, Z for undo, and the default case. Both Z and the default case don't correspond to a direction, so we'll do early returns on those. For the directional keys, we want to set our direction variable to the corresponding vector 2i, up for up, down for down, and so on. Then, at the end of the match case, we test to see if the player can move in that direction. And if they can, make them move. If we go into an empty scene, drag in our player, and hit play, we can now move around using the arrow keys. Okay, maybe I'm getting a little too excited. Because even though we have movement, it doesn't look great. The player snaps between different tiles in a very abrupt way. To make it less jarring, we want to make them glide from one tile to another, which we'll do using tweens. A tween is an object in Godot that lets you smoothly interpolate any of an object's properties from one value to another over a set period of time. We'll define a tween variable in movable. Then, in our slide function, we first want to swap the order of these two lines of code. That way we have room to animate them going from the first tile to the next. After we set tile, we declare a new variable called target, which stores the position we want the player to move to. This is defined in the exact same way as we defined position. Finally, we can initialize our tween and tell it to interpolate our position to the new one over the span of 0.08 seconds. This might seem really quick, but that's what we want if we're going for snappy, responsive controls. Running the game, we can see the player glides between different tiles. The next major feature we'll need for a Sokoban is walls for the player to collide with. There are many different approaches you could go with for implementing this. I am going to completely avoid using physics objects, or collision shapes, or anything like that. For a game like this, that's just complete overkill. Instead, we're going to be using a tile map layer, and checking whether a tile is empty or not when determining if we can move. So, create a new tile map layer node. The first thing we're going to do is go up to the top right here under Groups. Groups are a way of categorizing nodes together, even when they may be very far apart in the scene tree. On our tile map layer, we'll be adding the group level tile map and make it a global group for convenience. Next, let's go back to the node inspector and set up our tile set. Ensure your tile size is correct. My tiles are each 16 by 16. Then under terrains, create a new terrain called walls. Finally, to begin setting up each individual tile, drag and drop in the image with your wall tiles and let Godot automatically set it up. Under paint, we can now define our terrain. Here you paint the rules for how different tiles are supposed to connect together. I'm going to skip ahead to once I'm done with that. This is what it should look like if you're using the tiles I've provided. I changed the color used in the overlay so that it's easier to see. To help streamline level design, we're also going to go to this side panel and add in a new Scenes collection. This is a feature of tile map layers that lets you place nodes in your scene from the tile map itself. I'll call my collection Interactables and drag and drop my player scene into it. Now in our demo scene, we can delete the player node and replace it using the tile map. Under terrains, we can now also draw on our walls. If you set up the terrain system correctly, then as you add in new tiles, they should look like they connect together seamlessly, like this. So, we need some way to manage collisions between the walls and all the movables. I'm going to do this with an autoload script, which is a type of script that Godot will keep continuously running in the background of all your scenes. Create a new script called level that extends node. In project settings, globals, we can add our level script as an autoload. We first need to define two new variables, tilemap, which will store our level's tilemap, and movables, which will store an array of all of our level's movables. In our ready function, we'll connect to the scene tree's scene_changed signal to a function called level_changed. We will then call this function ourselves to make sure everything gets initialized at the start of the game. For now, all the level_changed function will do is initialize our tilemap variable with the first node in the level tilemap group we created earlier. Ideally, there should only ever be one level tilemap in existence at a time, which is why this is safe for us to do. With a reference to our tilemap secured, we can now define the function that will enable wall collisions. I'll call it isTileWall. It will take in the coordinates of a tile and return a boolean saying whether there is or isn't a wall there. It returns tilemap isn't equal to null, which makes sure the tilemap we have stored is valid, and tilemap.getCellSourceID of tile equals 0. If we go to the tileset tab, you can see the different tile sources and their IDs. We only care if there's a wall, which is why we're only checking for an ID of 0. With this helper function defined, we can finally implement wall collisions in Movable. To do this, we'll add a few new lines to canMove. Using the level global, we check to see if there's a wall tile in the direction we're trying to move. If there is, we return false because we don't want to be able to move through walls. Running our game, we can move around like normal still, but if we try to move into a wall-occupied cell, we're blocked. Now, you can't really have a Sokoban without objects to push around, so that's what we're working on next. Let's create a new scene called Crate that inherits Movable. I'll give it a sprite, and that's it. We won't need a custom script for this node. Before we can get to pushing it around though, we will need to add a bit more to the Movable class. Earlier, we defined an array of movables in the level script, but it isn't being initialized yet, so let's do that first. We'll override the enter and exit tree functions of Movable. In enter tree, we add the movable to the level array, and in exit tree, we remove it. These together should keep the array fully up to date with all the valid movables in our scene. Back to level, we'll create a function called getMovableAtTile, which takes in tile coordinates and returns a movable. This will loop over every node in movables, check if the node's tile matches the coordinates of the tile we're searching for, and if it does, return the node. After the loop, if we still haven't found a node, we return null. With this, we can now implement pushing. In the canMove function, after we've checked if there was a wall tile, we see if there's a movable on the tile we're about to go to. If there is, we return whether that movable can move in the same direction. In the move function, we do basically the exact same thing, except instead of checking if it can move, we just move it. Let's go to our test scene and add the crate to our tile set. I'll place a few around the scene. Running our game, we can test its behavior. First, we can push individual crates around. Second, if we line up a few crates in a row, we can push them all at once. And finally, if we try to push a crate into a wall, we are unable to. All as expected. Although this might not be as necessary, there is one more feature I'd like to add because I don't think any good Sokoban game is complete without it, and that's an undo button. The idea is simple. Every time the player moves, we create a list of every movable that's changed position and in which direction. Each time the player moves, we create another list. These lists will form a record of every move that's occurred over the course of the level. When the player presses Z, or whatever the undo button happens to be assigned to, we go through the most recent collection of moves and make each object move in the opposite direction to where it went last, effectively undoing the turn completely. We can keep doing this until everything eventually ends up right back where it started. So let's start getting this into code. First, we need to store each move. In the level global, we'll define a new class called move that will store a movable and a direction. Then we'll create a variable called passTurns that will store an array of arrays. Each of these subarrays will contain moves. In the level changed function, we'll clear passTurns because undoing moves from a previous level wouldn't make any sense. We'll also create a function for adding new moves called addMoveToTurn, which takes in a movable and a direction. It creates a new move, sets its variables, and adds it to the most recent array in passTurns. Next, we need to update the other scripts to make sure the passTurns array is up to date. In Player, before making a move, append an empty array to passTurns. This will be the array that stores all of the moves that happened this turn. In Movable, at the end of the move function, we'll then call addMoveToTurn, with the object itself and the direction it's moving in. We're now finished storing turns. There's a permanent record of every move the player makes, and every object that gets pushed along their path. Finally, we need a way to undo these turns. In Level, we'll create a new function, undoLastMove. This first checks that the passTurns array isn't empty. If it isn't, pop the most recent array of moves off of passTurns. For each move, we take the node in that move and call slide on it, with the opposite direction to what's stored. Again, this is why we made move and slide two different functions, because we don't want each undo to be counted as a full move. That would mean you could undo the undo, and then you get what I'm saying, not very helpful. Finally, let's go to player. Under the Z input case, we'll call level.undoLastMove before returning. Now all we can do is run our game and hope this works. Pressing Z before we make a move does nothing, as it should. If we move around a bit, push some blocks around, and then hit Z, it undoes correctly. We can press it a few more times. Sure seems to be working. And for the final test, if we just hold Z down, we should zip all the way back to the start of the level. And we do. Okay, now's an appropriate time for all the confetti and the music. Yes, maybe it's still all a bit much. In the description, I have the full source code of this project on GitHub. In that version, I've also added a few new features that you might want to look into. I'm DevPoodle. Thank you so much for watching. See you later, and goodbye! Oh, and in case you're wondering, yes, I do realize movable should actually be spelled like this, without the first E. I only realized this after writing the entire script and creating the whole demo project, and I just wish I had a real-life undo button right about now. Oh my goodness.